Something years.
Yeah. It's refreshing.
It's recording.
It's recording? Okay, so that's...
What's your major when you were undergrad?
Computational.
Oh, so you're not civil engineering?
No.
No?
Computational physics
Oh, okay.
and surface science.
Okay, so let's do it.
No.
So, welcome all those who decided to continue with this. And today's chapter 3. Molecular quantum mechanics. We had some simple systems last week, and now we're going to go to the good stuff, or at least get a little bit closer to it. Before we start with the molecule, we need to have an atom. And the simplest atom we can think of is the hydrogen atom, right? Or let's say hydrogen-like atoms. Everything's hydrogen-like, which has only a single electron, which makes things easy. So, and has only one nucleus. So obviously, what we have is our Hamiltonian. This is the kinetic energy of our electron. And this is the Coulomb attraction between the electron and the nucleus. Z is the charge of the nucleus. E is the elementary charge. You see we have many, many nice constants in our equation. And R is the distance between electron and nucleus. So to make things a little bit easier, and yeah.
So you're assuming that the proton doesn't move, right?
Yes.
So
right.
the proton is fixed and you are studying.
Exactly. We're just centering of the proton. We can use any reference, but this one is the one which makes most sense. It's like a universe with a single sun and a single planet.
And you put your coordinate system on the sun.
Yes. Yes. So we don't want to write all this stuff as this tons of constants all the time. So we define a nice reference system. For distances, we are working with Bohr's radius, which is defined like this. Everything here is constant, right? 4, pi, epsilon naught. Yeah.
Maybe a stupid question, but what is the Greek letter in the first term for the Hamiltonian
This?
equation? Yeah, the first term was the Greek letter to the power of 2.
No, this?
No.
H bar.
This
After that.
H bar.
No, this is the upside down triangle.
Okay, yes.
It's Nabla square.
Yes.
Oh,
Yes, this is Nabla squared.
Was that an operator?
This is the operator of the first derivative and squared you have.
It's
Versions
gradient
of
times
gradient.
gradient.
Okay.
The harmonic function.
Yeah, this is the divergence of the gradient.
So is that the first equation only for one atom or for 3 now? Because you're talking about the hydrogen, that's a H2O, right?
The hydrogen atom is just H.
Oh, yeah. I'm
One
sorry,
proton,
I'm talking
one
about water.
electron.
I'm sorry.
No, that's
Yeah,
too
you're right.
complex
So that's
for that.
okay.
That's already multi-electrons.
What you see is we have our constants and we sum them up and we get our Bohr's radius, which is more or less half an angstrom, roundabout.
Half an angstrom. Roundabout.
So the next thing is we do the same for our energy and we obtain the Hartree, which is just this. And yes?
The Hartree is a kind of energy, or
Yes, this is an energy. So we are measuring distances in multiples of Bohr's radius, energies in multiples of the Hartree energy.
where the Hartree energy? I mean, I don't know what is it. So, is it related with the electron charge or what?
It is just by this constant, just summed up, so that we have it so that everything turns out nicely and all the constants become one.
Basically, I mean, like you can express Hartree in terms of electron volts, right?
We can also express it in terms
How many
of
electron volts is 1 Hartree? Just to get some
That's a
idea.
good question. I don't recall the number. I'm so used to work with Hartrees. but I can tell you that it is 219,000 wave numbers from
I think it's 0.27.
How many electron volts is the ionization potential of hydrogen? Do you call this? This is 16 point something, right?
I don't know. Can you know that?
Must be something with 16 point whatever, and the Hartree energy is 2 times this value. So it's actually with 1 Hartree you can ionize 2 hydrogen atoms.
So one Hartree is 27.2 electron volts.
Yes, and half of this is 1 Rydberg. So 1 Hartree is 2 Rydbergs, and 1 Rydberg is sufficient to ionize a single hydrogen atom.
Basically to move the electron to the infinity, right?
Yes, yes. So what else we do is we define the electron mass as our reference for masses, and the elementary charge as our reference for charges. So E becomes 1, ME becomes 1, distance, 1 Bohr radius becomes 1, and an energy of 1 Hartree becomes 1. This makes things look much more nice. We don't need to write all this stuff, so it's looks pretty nice now. Of course, we can solve this equation in Cartesian coordinates, but we have a spherical problem, and it is just a horrible work to deal with a spherical problem in Cartesian coordinates. So we just go to spherical coordinates, and then our Laplacian takes this form. Looks less nice than in Cartesian coordinates, but is more easy to handle. And when we apply this, we obtain a wave function, which is, here we define this rho, which is then 2r by n is the quantum number, and a naught is our Bohr radius, just that we don't have so many constants here. It's just constant times r.
Okay.
So this is a normalization, and what we see is rho is a function of the distance r, so we have an entire term which just depends on r, and one term which depends on the angles. And these these are the spherical harmonics. Some of you might have seen them already. This part, this L with lots of numbers next to it, are general Laguerre polynomials. And yeah, this is just the E function, and N is our normalization of the wave function. So in principle, what we did is you solve this by separating. You separate the distance from the angles, and next you separate the angles. Well, in this case, you can also deal with them together. And as I have shown you last week, by simply multiplying all the independent coordinate wave functions into one wave function, we get our total wave function, right? Because it's separable, so they're multiplicative. So again, product. Our normalization depends actually on two of our quantum numbers, n and l, and it just ensures that the square of our wave function is integrated to 1.
Could you please elaborate on these two quantum numbers?
I
Where are
will
they coming
elaborate
from?
on all 3 of these. So, when we just go back, let's do some sketching. We know that at n equals 1, we are in our ground state. This means 0 nodes, right? Last week we had the concept of a node, which is that the wave function becomes 0 in between its boundaries. So, if we would just look at this exponential part, we wouldn't have any node, right? That's just an exponential. So obviously this is what we should get for n equals 1. Next thing is we see this polynomial, rho to the power of L, which is our next quantum number. Well, with this, with L equals 1, we have one node in spherical symmetry. So if we would cut through our wave function as a sphere, what we would see is that we start with some kind of, so here's our center, here's our distance. We start with a positive sign, then we change our sign, getting negative. If we have two nodes just in the distance, we change sign again, and so on. So this is just the distance part. Now interestingly, we have n, which starts at 1, 2, well, till we are infinite. And L is then n minus 1 at a maximum. N minus 1, minus 2, whatever, till it becomes 0. With n equals 1, we automatically just have n equals 0. Later on, it allows us to add more nodes to this. And finally, the spherical harmonics, they also have their own quantum number, m. M goes from, well, L minus 1 to minus L. Okay? So what does it mean? Well, obviously we have different ways to construct our nodes. One way I showed you. The next way is we have n equals 2. Which means that we need to have one node. But at L equals 0, we obtain this. So how do we obtain our node? Well, simply by using this, m. In this case, it would also be m can only be 0. So we have a little problem with our nodes at this point. Unless we also take this part into consideration, this polynomial, which also multiplies it. So if we have L equals 0, this polynomial is just the first order polynomial. So we get this again. The next one is then n equals 2, L equals 1. This immediately brings our Laguerre polynomials to a constant. Radially, we are here. But with L equals 1, our spherical harmonics are becoming something different to a constant. Know that the spherical harmonic of 0, 0 is a constant. So here we start now with some angular terms. And these are looking like, we're here in our angles, or projected into Cartesian coordinates. It would look like having one like this with a change of sign, or one in the x direction or one in the z direction. This is what we then know as p orbitals. So L equals 0 means an s orbital. L equals 1 is a p orbital, 2 is a d, 3 is an f, and we can continue this in principle. So here we're growing. So n tells us on which shell we are. L tells us which kind of orbitals we are facing. And m further specifies in which direction. So what we see is we build the entire picture. So for example, we take this, we go for, say, n equals 3, L equals 1, m equals, say, 1. 2 nodes, right? What we obtain is our distance. Well, in principle, from our sphere, we would know that there is 1 node left, because 1 is consumed by the L. And what we also know is that we have an L of 1, so we are in this kind of p orbital. So what we actually see is something like this. Plus, minus, and plus, minus. This is our orbital for this case. Yes?
For the first case, those 3 circles, so what is plus?
This is the case then. We have 2 nodes. So this would be the case for n equals 3, L equals 0, L equals 0. This is then this case. We can go one step further. We can even go to L equals 2. In this case, we do not have any radial nodes. We just have spherical nodes. And this would be a d orbital. So this would be, for example, something like this. 1 node and 2nd node.
What do you
And
mean?
not in radial.
What do you mean by plus minus? Like,
This is the sign of our wave function. So here we see our nodes pretty clearly. It just works like this. Yes.
If L is 0, you would obtain the first graph, right?
Yes.
And it's exponential.
Yes.
Okay.
Yes.
Just,
With the exception of those where L is 0, but
but then cannot be a
n is greater than 1, because then the Laguerre polynomials are getting values which are different.
Okay.
So when we're getting our polynomial expansion there, we also get our node.
Could you please explain one more time that for the case n equals to 3, L at n equals to 1, why do we get larger orbitals over there?
On the outside?
Yeah.
Because, well, we do not have the standalone, right? We need to fill our orbitals from the beginning. So in the inner shell, we already have one at n equals 1,
Okay.
which is consuming density. So they need to be larger to avoid Coulomb repulsion with the other orbitals.
Okay.
Because it's also, we start in the lowest energy orbitals, and from there we fill them up. So we have these centered inner shell orbitals already, and then we go to the outer shell. So this means that inside the inner node we have less density than in the outer.
Okay.
So far, so nice. Our energies, unless we apply an external electromagnetic field, just depend on the quantum number n. There is no L dependence. This gives us something interesting to see, because if we have n equals 2, L equals 0, M equals 0, it is the same as the energy of n equals 2, L equals 1, M equals 1, which is the same, and so you can complete this. So, we are calling this in quantum mechanics degenerate energies. We have several orbitals which belong to the same system, which yield the same energy. So these are degenerate orbitals, and they are yielding to degenerate energies. This means that there is no more a bijective mapping between energy and orbital, or energy and quantum number.
So we have a 3D system, and that's why we have 3 quantum numbers to describe the wave function. But since Hamiltonian only depends on R, the energy only depends on 1 quantum number.
Exactly.
And that's the origin of the degeneracy of the system.
Yes, right. You can also get easily degenerate energies for particle in the box, for example. If you have both box lengths being identical, then you're automatically going degenerate as well. And so it always, the higher your dimensionality is, the higher is the probability that you are meeting degenerate orbitals. They don't even need to be at the same place of a molecule.
This degeneracy is, you have shown it for hydrogen atom, but what happens if you have multiple electrons? Is it going to be again degenerate?
Then of course it can become more degenerate. Easiest example, benzene. With benzene, you have the highest occupied molecular orbital, or orbitals, which are 2 of pi character, and they have the same energy. And the lowest unoccupied molecular orbitals are of pi star character, anti-bonding pi orbitals, and they also have the same energy. So you immediately have, at both sides of the occupation border, 2 degenerate orbitals. And for larger aromatic systems, it may even become much more. So our wave functions are normalized so that this full integral over full space means that we obtain a 1 if they have the same quantum numbers, and if any quantum number differs, we are getting 0. Sure, we need the same wave function to form this square so that we have our density. And we don't want to write this integral all the time. So this is why we are going to Dirac notation. It shortens things quite a lot. It's also called bracket notation. So we just need to enter the wave, the quantum numbers here, or whatever characterizes our wave function, right? We just need to be sure what it is, and then we have a bra vector and a ket vector plus some operator c, so we have a bracket, just like this, and this gives us the expectation value of c with these 2 wave functions. So, in principle, we can work with this. So this one is the complex conjugate part, which is the bra, and the ket is then the right hand part of this integral, right? So this also means that complex conjugate is, well, if we have the complex conjugate of this, then this one becomes non-conjugate, and this one's conjugate. So, in this case, the bra becomes the ket, and the ket becomes the bra. Simple. Just like this. We can shift. It makes things much less complicated as soon as you're getting used to it. Of course, one always needs to keep in mind what are our wave functions, what are our quantum numbers Even more important, this is one wave function. What if we have two wave functions? Then we need to understand already here that each one is belonging to a certain set of coordinates, to a certain dimension. And we number our dimensions from the lowest to the highest, and here again, lowest to highest. So if this would not be r, theta, and phi, just x1 to x10, then it would be the one for x1, for x2, x3, and so on until we reach x10. And the same on the other side. We always sort by coordinates. So the higher the rank of our coordinate is, the more to the right we are, in the bra as well as in the cat. You always need to keep this in mind, because this information is not explicitly here, but implicit. And this makes our Schrödinger equation appear much, much nicer, right? It's just like this. This is then wave function with our Hamiltonian. Well, we can work on this. It was just like anything in linear algebra. We have a sum, so the integral over a sum is the sum of the integrals. Holds true. Well, 1/2 is a constant. We just can put it outside. Same as the z. Everything that's to be integrated stays inside. This is then, in this case, our operator, we can have it work to both directions, right? Our operator may work to the left as well as to the right. So we see, if it works to the left, it is En. If it works to the right, it is En prime. Both is a constant, which means that this integral needs to be 1, or we obtain a 0. So we do not obtain any of these. In the first step, yes, but if they are not identical, we immediately go 0. We have to, because otherwise we would state that for any quantum number n, we obtain the same energy as for another quantum number n prime, which is not the case in general. So, this is how our Dirac's notation works. And I will keep working with the Dirac notation for the complete lecture, because I'm not going to write thousands of constants in my equations. Okay? You should try to get used to this. Now we have our hydrogen atom and we can go to molecules. This is slightly more complicated. So what we see is we sum over all kinetic energies of electrons. We sum over the Coulomb attraction between electrons and nuclei. When I'm using the sum large, a capital letter, then it means nucleus, and it's an electron otherwise. Makes things easier.
So just to try to get the big picture, you have multiple nuclei, right?
And multiple electrons.
And multiple electrons,
Yes.
right? So you are calculating the interaction between each electron and all the nuclei, right?
Yes, right. So every electron I faces a certain attraction depending on its distance to the nucleus, and to also depending on the charge of each nucleus. So that's a positive Coulomb force, sorry, negative, so it's attractive. Then we are going repulsive, electron and electron. Each electron faces a repulsion of each other electron. All right? Next, we have the kinetic energy of our nuclei. Here, their masses are multiples of electron masses, because our electron mass is our reference. So even the hydrogen has something like 2,000 of the mass, the nucleus. And finally, the repulsion between the nuclei. Well, that's quite a lot what we have in our system. Good thing is that Born and Oppenheimer make an approximation, because the electrons have much less weight and they're moving much, much faster than the nuclei. So this means that one can consider that the nuclear positions are static with respect to the electrons. So whenever the nucleus, any nucleus moves, the electrons follow instantaneously. Because it's just, it's moving so much slower than the electron that it can follow immediately without any big loss in time. So in this, if this is the case, then our repulsion of the nuclei is just a parameter. It's just an offset for our total energy. We can add it later on. We don't even need to work with it in our computations. The same thing is that the electronic energies, that the kinetic energies for the nuclei are also neglected. Sure, I mean, they are considered static with respect to the electrons. So their kinetic energy is zero with respect to electrons. However, all this is getting back together when we are going to compute the potential for the potential energy surface, for example. So if we have two nuclei and we want to get the vibrations, when they are at equilibrium distance, we get a minimum in our total electronic energy plus nuclear repulsion. And then we change our distance between the nuclei, and this yields, of course, different nuclear repulsions, but also different electronic energies for the system. And if we have this potential, and then take our kinetic energy of the nuclei back, this operator, we obtain the vibrational and rotational energies of our system. Because in this part, here as soon as we add the kinetic energy, we have couplings between vibrations and the potential energy surface. So we can run, by just changing our distance between the nuclei, we can get the potential energy for the movement of the nuclei, which is just the repulsion between two atomic cores and the electronic energy of what remains in the system. This is pretty nice, and for small systems you get very accurate potential energy curves. For larger systems, well, you see that it's quadratically scaling. Then we make our Hamiltonian a little bit less complicated. Number one is, obviously we have some kind of one electron terms and two electron terms. Our one electron operator is then our electron in the potential of all the nuclei. And we can sum over all electrons, but it's just a single electron. So we just call it like this. This makes our Hamiltonian a little bit less complicated. But, unfortunately, each electron depends on the position of all other electrons because of this part. So, we somehow need to find a solution to this. It is non-linear. We need to go there iteratively. But maybe we can just see what happens if we just take one electron and keep the others constant. And further on, we consider that each electron is described sufficiently by a single quantum number. Well, in this case n for each electron. Right? Each electron is in a unique orbital It has unique energy and we are only after the energy. We can also define some kind of ordering of our NLM so that we start 1, 0, 0 is quantum number 1, 2, 0, 0 is 2, 2, 1, 1 is 3, and so on. So in principle we can map. So we are getting such a nice Hamiltonian. N is our selected electron. And what we already have assumed is that our wave functions are orthonormal. They are well normalized. And that they are eigenfunctions to this Hamiltonian. Okay, so looks like it can work. Integrate over the entire system. Now each electron, we sum over all our electrons and integrate over all of them. Then we have 2 electron wave functions as a large sum. Well, this is our 1 electron operator. This is our Coulomb repulsion. And we have the sum of all orbital energies. Until now, we assumed that all our electrons have some kind of unique marker. We directly know, okay, this is electron 1, this is electron 10, this is electron 5. This is not the case in nature. Each electron looks the same. So they are not distinguishable. So we need to solve the 2 electron integral for both cases. One where electron I is in the coordinates of electron I, so its own coordinates, and one where it is in the coordinates of J. And vice versa, because we cannot distinguish. So we cannot say which one is which one. We can define a kind of permutation operator. As that, we are sorted by the coordinates. This is I in the coordinates of I, J in the coordinates of J. We permutate. We have J in the coordinates of I and I in the coordinates of J. If you permutate again, we should get our system back. So one permutation leads to something. Second permutation leads to the same system because we permute back. This is only fulfilled in this case. Otherwise, we would get some kind of constant in front of it. The positive solutions to this are bosonic, and the negative solutions are fermionic. You can look at quantum statistics for a full derivation of this, but it's not necessary to understand. So what we have is we permute once and we get the negative. So we have a minus here in front of this. In this case, when we have to check for both possibilities, this integral or this sum is actually 2 sums. One where we have, well, we integrate in each coordinate system. So this is a J, Coulomb operator J, and then we integrate in the coordinates of I, the same. Or we have this weird thing that we permutated. So I is now in the inner integral, and J is in the outer integral. This is a little strange, and this is a truly quantum mechanical effect. So our Coulomb operator splits out into 2 operators. And we can define them together with a wave function. That this operator, where we do not permute, we call the Coulomb operator. So every electron faces the mean field, because this is what this integral means, right? We integrate over all the possible positions of J. So this is the mean field of all other electrons that we're experiencing. And then we have this exchange, where we also get some kind of mean field. And this yields our Hamiltonian for the system. 1 electron plus Coulomb minus exchange. The minus comes from the permutations.
So I think I understood this the term up there, right? Which is each electron is somehow immersed in like a mean field effect of all the other electrons that are in the system. But what's really the point behind this exchange of the
Well, this exchange is.
what is physically? I mean, can you?
Physically, this is a good question.
Yeah.
Well, in principle, it comes from this quantum mechanics, so that by correlating our electrons, we obtain a second operator with the opposite sign to the Coulomb. So whatever value we have in this operator, we are obtaining a kind of attraction between the electrons, which is indeed the case, but only, when you can see for this even later, when we add the spin, then we get a true attraction if they have opposite spin. If you do not add it, it simply gets 0.
Oh, so this is basically in each orbital, you have an electron with a spin downward, the other one upward, and these have affinity to each other. So
Yes.
to model that thing, right, we have to have some sort of an operator that can put two electrons together in one orbit.
Yes, because otherwise we are with fermions.
Otherwise they are going to have
just
repulsion, right?
Yes, otherwise the repulsion would get infinite in the same orbit.
Oh, that's cool.
Then it would be thrown out. Yes.
Is this what really happened in reality, or just?
This
for-
is a real effect, yes. You can see this effect of opposite spin in one orbital that it has a stabilizing effect.
Okay. Thanks.
So this is real, although it just came from the mathematics of the permutation.
So even though we didn't consider spin so far, but we see the effect.
Yes, we have this operator still, although we don't have spin. But when we solve it, we see that it just has no effect unless spin is added.
But the spin would only tell you which direction is the rotation and so on.
Yes, but the total spin integrals are giving values for both. Typically in Hartree-Fock, we will see that typically this is about half the value of this one. So whenever we occupy a spatial orbital by 2 electrons of opposite spin, then we would immediately reduce our repulsion. If we try to put the same spin into one orbital, then our electrons would just immediately face maximum repulsion. So it's unstable.
So you said that excluding spin, the exchange operator will give like 0 value?
It should get towards 0, yes.
So is it because the value of the bracket is 0, or?
Yes. Yeah. So it starts to get to 0 out here, or at least getting close to 0. So we have started with a large Archie Hamiltonian, and now we have such a nice one. Unfortunately, we still don't know how to obtain our eigenfunctions, right? We have a little problem with this, and we know that it is nonlinear. So let's try variation in principle. I think this equation is well known. We have some trial wave function, and we have the exact wave function, and this is just what we all know from Rayleigh-Ritz variation in principle. I hope some of you have seen this before.
Who has seen Rayleigh-Ritz method? This will find finite element.
Okay.
So you have to probably explain it.
Okay, so in principle, this is a theorem which is proven that when we know the exact state of a system, and we try to approach this by varying the function to describe this state, then we can just look at any variation, and whatever variation we find, we can never get below the energy of the exact solution. And this is good to know, because it means that however we vary, we cannot get artificially low in energy. We have a lower boundary to our energies. And this, of course, makes it a little comfortable, and we can just watch our variations. So the lower whenever we're getting lower in energy, we get a better wave function. And when we don't get lower anymore, we have reached a wave function which is equivalent or identical to the exact wave function.
Basically, you are using this method to calculate the ground state, right?
Yes. So we want to get the ground state correctly. And the good thing is, we can have a full basis of these trial functions, right? We can try several of them. And we also know that this yields us some kind of matrix. We have just these elements for any trial function. We construct a matrix out of it, and we diagonalize it. And the diagonal matrix yields the eigenvalues to this problem, and the eigenvectors. And if we want the ground state, we pick the lowest energy eigenvalue and the corresponding eigenfunction. So what we can do now is think of taking some kind of atomic basis function, which are hydrogen atom-like. Yeah. And then we can construct our Hamiltonian. These matrix elements Ij are all hydrogen-like basis functions. And we just need to diagonalize. And we obtain our orbital energies in the diagonal matrix, and our eigenvectors are our molecular orbitals, described as some kind of expansion coefficient times basis function. And we sum overall, and we get the correct basis function, orbital function for our molecular orbital. So this is a very simple thing. So we can just do what we also do with finite elements, for example, and we obtain the solution, which is nice. As an example, let us have a look at the minimal basis hydrogen molecule. So we start with the wave functions of the hydrogen atom. Now we just sum the constants a little bit. We want to have the 1s function, right? We are in the ground state with our hydrogen atoms. And all the constants are summed into new constant zeta. Then it takes this simple form. Okay, there's a normalization in front of it still, but beyond that, it's just the simple form. E to the power of minus zeta r. Simple. We have two hydrogen atoms. This means that we center the 1 at the coordinate center of hydrogen atom 1, which we then call R1, and the other ones at R2. So we have two hydrogen atoms. Each one is centered at its respective coordinates, at its respective hydrogen atom, and we obtain this Hamiltonian. This is our 1 electron Hamiltonian. We don't need to write a 2 electron wave function for this, because we know it is 1 electron. So the second part is simply the integral, and the integral is simply 1. Right? The solution of the hydrogen atom, so the integral conjugate wave complex conjugate wave function times wave function is automatically 1. And then we further reduced our writing. We have this exchange, we have this Coulomb exchange, short notation. So wherever you have this, it means that you have your Coulomb operator and your exchange operator. So what we have here, we have our 1 electron part and the 2 electron part on the diagonal. Of the diagonal, we only have our Coulomb and exchange part, because there is no 1 electron part in the off diagonal, because there are 2 different electrons only. So this is 0 plus this part, and here again. We are symmetric and Hermitian in our matrix. And then we diagonalize all this and we obtain this part. This is how it should be. So we look at some solutions. Well, when you ever diagonalized such a 2 times 2 matrix, which is symmetric, you will find out that your solution is pretty simple. Your rotational matrix just has a form of, can you make it easier? That's it. Not sure if I rotate it in the right direction, otherwise the -1 needs to be here. But in principle, that's the solution. Okay, so when we have this, we can apply it to our basis functions, right? We get a first one, 1 by square root of 2, and the plus, which is simple. And we have the same as a minus in between. This one corresponds to an energy which is lower than the individual energy of our original atomic wave function. We call it the bonding orbital, and in this case, as we have full rotational symmetry around our bonding axis, it is a sigma orbital. So this is sigma, and then we have sigma star, which is anti-bonding. And this is a negative linear combination. With hydrogen, it's a nice case because it goes down the same amount as it goes up the other way. And this is a favorable situation, of course, as 2 times 1s yields more energy than 2 times sigma, because 2 electrons are now in the sigma orbital. As soon as we would excite and take 1 sigma to a sigma star, our energy would be the same as this one, and our bond would dissociate. So we can have resonant breaking of a bond. And we can have a look at these wave functions. So this is where the first atom is centered, H1, and it has this wave function there. Okay, you see this, it is r to the minus, e to the minus zeta r. As it is symmetric, because we are in a spherical symmetry, it just goes down on both sides. Same for the second one. And now our sigma orbital looks like this. So we have a shared electronic density. This is what it means. Right? When we look at the density, we see that it is shared, whereas the sigma star has a node. And this tells us 2 things. Number 1, obviously, molecular orbitals follow the same rules as any other orbitals. Ground state, no, 0 nodes. Next one, 1 node. One thereafter, 2 nodes, and so on. So we still have nodes. It still works just the same as everywhere in quantum mechanics. But we see that there is a place in between those atoms where we have an electronic density of 0. This is not a problem in general, but in this case it is. And the more electrons we have, of course, then the more nodes we have before we get anti-bonding. Okay, so we can conclude that a positive overlap of atomic functions yields a chemical bond. And a negative overlap yields an anti-bonding orbital, which means, well, actually it means more nodes than we have in our occupied space. This is just true with one node, it is true for a hydrogen molecule. We know that anti-bonding orbitals are higher in energy than the atomic orbitals from which they formed. And this means it is thermodynamically totally unfavorable to occupy them. And we also have the case in principle that there is no overlap at all. So this means we obtain a non-bonding orbital. This has no direct effect on bonding because it is non-bonding. But it still has an indirect effect. It still has Coulomb and exchange interactions with all the other orbitals around. So it may either stabilize or destabilize neighboring bonds.
Is that related with the resonant position that a molecule can have?
Yes, so it's especially related with, for example,
Like the resonant effects in an benzene, for example?
no, this is not for non-bonding, but this is especially for forming complexes.
Okay.
There you have the non-bonding orbitals, which are in the complex and which play an important role, especially for the symmetry of the complex. And it also plays a role, for example, when you have resonances in heteroaromatic systems, where you have the lone pairs, which are non-bonding. They are non-bonding, but they still interact with everything else. So this is a little first sight on chemistry here. I think this is enough for today. I don't want to overload your brains.
Do you give homework? Maybe
Well,
they can take like 2 of these atoms from infinity and then plot the potential energy as they make them close
yeah,
to each other.
you can do this. I mean,
Yeah,
you
it's
just,
very
you just
simple.
do something like this, right?
They plot the potential energy to see that whether they
No,
get
not,
some
I
sort
wouldn't
of
take the potential energy. I would just take this one like the wave function just to see when you find a place where it becomes 0 in between again. And yeah. You have the recipe to construct your wave functions, and you have your wave function. Everything. And in principle, okay, it's difficult to compute these integrals. I wouldn't recommend doing this by hand. You can. There is an analytical solution for individual orbitals, at least, but it's a hell of a work. So if you want to spend a day with this, you can do. It's yeah, quite a lot. What one can, of course, do is just diagonalize some matrices, just for fun, just to find out how it works. And yeah, in principle, short brief look at Jacobi diagonalization does not hurt. Indeed, it helps to understand what's going on. And this is a simple case, but when we have like 10 times 10, 100 times 100, one still should know a little bit about what the diagonalizer is doing.
What are we gonna do next session after?
Next section will then be Hartley-Fock, which is a direct continuation of this. Actually, this is already the Fock operator. So we will work then with ideas like we have a closer look on basis sets. We have a closer look on how to iteratively find solutions to this. And finally, we will have a look on correlation, which directly leads to density functions. So we will meet Hartree Fock in the next session, and we meet the point where Hartree Fock fades. And it doesn't just fade a little bit, it just fades horribly. Good. Okay.
Awesome. Thank you.